And question number was, one second, question number 9. It was asking number of distinct bases of a two-dimensional vector space over Z3. So whenever I will be asked to find number of distinct bases of a two-dimensional vector space over Zn, then formula is, over Zp, then formula is p to the power n minus 1, p to the power n minus p, so on till p to the power n minus p to the power n minus 1 divided by n factorial. Now here n denotes the dimension, so dimension is 2 here, and p is 3. So simply put this, 3 to the power 2 minus 1, 3 to the power 2 minus 3 till here only, and divided by 2 factorial. So on solving, 9 minus 1, 8, 9 minus 3, 6, upon 2. So answer is 24. Means option A is correct. And in the next question, total number of ordered bases of the vector space V3Z3. Now here formula will be same, but this n factorial term, this term will not be there. Means formula will be p to the power n minus 1, p to the power n minus p, so on till p to the power n minus p to the power n minus 1. Here n is 3, p is 3. It is like this Vn Zp. Dimension is 3 here and p is 3. So 3 to the power 3 minus 1, 3 to the power 3 minus 3, 3 to the power 3 minus 3 square. 27 minus 1, 26. 27 minus 3, 24. 27 minus 9, 18. So this will be 1, 1, 2, 3, 2. So answer is option A. Next question. U is given as spanning of 1, 1, minus 1, 2, 3, minus 1, 3, 1, minus 5. V is given as spanning of 1, 1, minus 3, 3 minus 2, minus 8, 2, 1, minus 3. And we are asked to find U intersection V. So firstly, what you can do here is you can form the linear combination of these three vectors, alpha 1, 1 minus 1 plus beta 2, 3 minus 1 plus gamma 3, 1 minus 5 equal to 0, 0, 0. So you will get alpha plus 2 beta plus 3 gamma equal to 0, alpha plus 3 beta plus gamma equal to 0, minus alpha minus beta minus 5 gamma equal to 0. Now if I add these two equations, I will get 2 beta minus 4 gamma equal to 0. Means beta is 2 gamma. And from here I can find alpha, minus 2 beta minus 3 gamma. So minus 4 gamma minus 3 gamma. This is minus 7 gamma. So U can be written as spanning set of minus 7 gamma, 2 gamma and gamma. And gamma will be any real number. Similarly for V also, alpha times of 1 1 minus 3 plus beta times of 3 minus 2 minus 8 plus gamma times of 2 1 minus 3 equal to 0 0 0. So alpha plus 3 beta plus 2 gamma equal to 0. Alpha minus 2 beta plus gamma equal to 0. Minus 3 alpha minus 8 beta minus 3 gamma equal to 0. So if I add these two equations, I will get 2 alpha plus beta plus 3 gamma equal to 0. And third equation was minus 3 alpha. Here it was alpha. Minus 8 beta minus 3 gamma equal to 0. So this will be minus alpha minus 7 beta equal to 0. So alpha can be written as 7 beta. Now I can find gamma from this second equation, minus alpha plus 2 beta. So this will be minus 5 beta. U intersection V. यहाँ से ऐसे भी देख सकते हो कि जो ये कंडीशंस मैंने निकाली हैं, एक ये वाली और एक ये वाली, ये कंडीशन कब सेटिस्फाई होंगी? अगर गामा को 0 लिया जाए तो अल्फा भी 0 आएगा, बीटा भी 0 आएगा, ऐसे देख सकते हो ना?
यस मैम।
और सिमिलर मैनर में यहाँ पे भी अगर मैं बीटा को 0 लूंगी तो अल्फा भी 0, गामा भी 0, क्योंकि बीटा पर डिपेंड कर रहा है। सो अगर उसका इंटरसेक्शन देखोगे ना तो वो u के इक्वल आएगा ना वो v के इक्वल आएगा, 0 के इक्वल आ रहा है हमारा, 0 सबस्पेस के इक्वल। सो ये 0 सबस्पेस के इक्वल होगा। लास्ट क्लास में कहाँ तक किया था हमने?
लीनियर ट्रांसफॉर्मेशंस की थी, 1 and 1 1 1 on 2 फंक्शंस। अब इसको हम डायरेक्टली मैट्रिसेस फॉर्म में लेके करें तब नहीं हो पाएगा ये, दोनों की जैसे हम कॉम्बिनेशन को एक ही मैट्रिक्स में करके फिर एक्लियन रो एक्लियन फॉर्म में कन्वर्ट करते हैं। देन
फिर डायमेंशन देखें।
Yes.
ऐसे
जैसे
करके
ये
ऐसे कह रहे हो 1 1 -1
1 1 -1, then 2 3 -1, 3 1 -5.
2 1 -3। अब इसके नीचे की एंट्री 0 बनानी है, सो रो ऑपरेशन विल बी R2 टेंड्स टू R2 - 2 times of R1, R3 - 3 times of R1, R4 R4 - R1, R5 minus 3 times of R1, R6. So this is pivot element. Now we need to make entries below this pivot element 0. R3 tends to R3 plus 2 times of R2, R4 is as it is, R5 plus 5 times of R2, R6 plus R, R3 plus 2 times of R2 0, R3 plus 5 times of R2 3, 1 second, R3 plus 2 times of R2, this and R4 was as it is, means -2, then 0 0. So इसको अगर वापस से लीनियर कॉम्बिनेशन में लिखूं, वही हो गया ना। गामा इज 0 मीन्स बीटा इज 0, बीटा इज 0, गामा इज ऑल्सो 0, सो अल्फा इज 0। वहाँ से भी सेम आ गया। क्लियर है?
Yes, ma'am. Clear.
Now next is product of linear transformation. So if I have a linear transformation like this, T1 is a mapping from R cube to R4. In matrix form, it is a matrix of order 4 cross 3. Means whenever I have been given a matrix of this type, means it is a linear transformation from R3 to R4. Means number of columns to its number of rows. Another linear transformation T2 as R4 to R5. So its matrix will be 5 cross 4 order. Now I need to check whether T1 composition T2 is defined or not. So firstly, I will see T2. T2 is R4 to R5 and then T1. And T1 was R3 to R4. This is not possible, no? It is not possible because if it was R5 then it is possible. Means T1 composition T2 is not possible, but if I take T2 composition T1, T1 is R3 to R4, then T2 is R4 to R5. Now it is possible. Means T2 composition T1 will be a matrix of order 5 cross 3. Means this was B and A of order 5 cross 3. Now we will see some results for this also. If F is 1 1 and G is 1 1, this implies G composition F is 1 1. Second result, if F is onto and G is onto, this implies G composition F is onto. If F is bijective, means both 1 1 and onto, and G is bijective, this implies G composition F is bijective. But converse is not true. G composition F is bijective, then we will always say that F is 1 1 and G is onto. One question on this. Let S be a mapping from R4 to R3 and T be a mapping from R3 to R4 be two linear mappings, then T composition S is 1 1 but not onto. Second, T composition S is onto but not 1 1. Third, T composition S is 1 1 and onto both. So firstly see T composition S. S is from R4 to R3. T is from R3 to R4. That is T composition S is a mapping from R4 to R4. So if dimension is same, dimension of domain and codomain is same, then T composition S can be both 1 1 or onto, or I can say neither 1 1 nor onto. So by this, options 1 and 2 are discarded. Whenever dimensions of domain and codomain is same, then I can say that they will be 1 1, they will be both 1 1 or onto. Means they will be simultaneously 1 1 and onto, or they will be simultaneously neither 1 1 nor onto. So from this I can see that by this result, if T composition S is both 1 1 and onto, it means that S is 1 1 and T is onto. But what was my S? R4 to R3. So do you remember this, like if cardinality of domain is greater than cardinality of codomain, then it can be onto, but
You
not both.
cannot.
So this will contradict this, na? That S is 1 1. Means S is S is 1 1. This is not a possibility, है ना? And T is mapping from R3 to R4. And cardinality of R3 is less than cardinality of R4. So this can be 1 1 but not onto, na? And in C part it was saying that T composition S is 1 1 and onto both. So it is not possible, na? Because I am getting a contradiction on this. S is not 1 1 and T is not onto. So option 3 is also discarded, na? So answer is option 4. Is this clear?
Yes, ma'am.
Now next is a small concept of dual space. Let us discuss that too. Let VF be a vector space such that dimension of V is n. T is a mapping from V to F. Now in dual spaces I will talk about linear functionals. What was the difference between linear transformation and linear functionals? Hmm?
Linear operator we have studied कि domain and codomain will be of same dimension, but linear functional we have not studied.
Basic difference between linear transformation and linear functional is that in linear transformation T is a mapping from a vector space to another vector space. In linear functional it will be a mapping from a vector space to a field. Difference is in this codomain. In linear operator, T is a mapping from a vector space to itself. Now is it clear?
Yes, ma'am.
Property will be same, but only difference is in this codomain part. So dual space is defined by V star. Basically, dual space is a set of all the linear functionals from a vector space to a field. So as I have taken dimension of V as n, so dimension of V star will also be n. And if I denote V1, V2, Vn as ordered basis of V, then V star denotes ordered basis of V star. For example, and one more thing, these Vi stars will be a mapping from a vector space to a functional. These are linear functionals. Do you know what is Kronecker delta?
That is one if del I is 0. Sorry, the one, then otherwise 0.
If Vi star Bj is there, then it will be 1. If I is equals to j, 0.
Yes.
If I is not equal to j,
Then it is 0.
This is Kronecker delta. For example, V is equals to R cube. B is U1 equal to 100. U2 is 110. U3 is 111. And B star means basis of dual space is defined as F1, F2, F3. And linear functional is defined as F A B C is equals to A plus B plus C, where A B C belongs to R cube. And if F is equals to alpha 1 F1 plus alpha 2 F2 plus alpha 3 F3, then I need to find alpha 1, alpha 2, alpha 3. And options are 1, 2, 3, 1, 3, 2, 2, 3, 1, 3, 2, 1. So firstly, FU1. Simply you need to put this basis elements in this given functional. So FU1 means F100. So A plus B plus C. This will be or you can put it here also ना FU1 वैसे तो सेम ही आएगा अल्फा 1 या फिर ऐसे ही करो F1U1 F1U1 तो ये आपका 1 आएगा और वैसे भी 1 ही आना था क्योंकि I और J इक्वल है ना क्रोनेकर डेल्टा डेफिनेशन देन F1U2 simply I is not equal to J so 0 F1U3 0 F2U1 what will be F2U1
जीरो।
and from here also F is equals to alpha 1 F1 plus alpha 2 F2 plus alpha 3 F3 so if you see FU1 means alpha 1 F1 U1 plus alpha 2 F2 U1 plus alpha 3 F3 U1 so this will be 0 this will be 0 this is 1 and FU1 F1 0 0 so from here A plus B plus C because FABC was defined as A plus B plus C so alpha 1 is 1 FU2 so alpha 1 F let me write it completely alpha 1 F1 U2 plus alpha 2 F2 U2 so from here FU2 F110 this is also 0 this is also 0 this is 1 alpha 2 A plus B plus C alpha 2 is 2 now lastly FU3 alpha 1 F1 U3 plus alpha 2 F1 U3 alpha 3 F3 U3 so from here FU3 F111 alpha 3 is 3 so alpha 1 alpha 2 alpha 3 will be 1 2 3 so answer is option A. Now next is invariant subspace. So let T mapping from V to V be a linear operator. Let W be a subspace of V. Then W is said to be invariant under T if TW is contained in W. For example, T is a mapping from V to V. T1 is a mapping from R square to R square, defined as T1 x comma y is equals to 0 comma x. T2 is a mapping from R square to R square. T2 x comma y is equals to 0 comma y. And subspace is given as so I need to check invariant subspace means TW should be contained in W, or I can show that TW belongs to this subspace for all W belongs to subspace. So any element of this subspace is of the type Wx comma 0. What will be T1W? T1x comma 0. It will be 0 comma x na? Na? 0 comma x by this definition. And this does not belongs to W na? Because in W y is 0. Here I am getting x as 0. Similarly T2W T2x comma 0. So this will be T2x comma 0. 0 comma 0 na? है ना? 0 comma 0 na?
Yes, y0 हो गया ना?
This belongs to W means W is an invariant subspace of T2 but not of T1. Now change of basis matrix or transition matrix. Let E1, E2 so on till En and E1 dash, E2 dash so on till En dash be two arbitrary bases of a vector space V over a field F. We can suppose that Ei dash is equals to summation j equal to 1 to n aij ej. Means I am able to write Ei dash as a linear combination of these basis elements where aig are scalars, so it belongs to field, that is Ei dash is equals to ai1 e1 plus ai2 e2 so on till ain en. putting I equal to 1 to n, we get the following equations. E1 dash will be A11 even, E2 dash is equals to A21 E1 plus A22 E2 A2n En. So coefficient matrix is A11 A12 A1n A21 A22 A2n. Now by taking the transpose of this matrix, I will get the transition matrix. From the old basis to the new basis, so as E1 dash, E2 dash, so on till En dash is Li set because it was the basis now, and hence the inverse of matrix P exists. And P inverse will be the transition matrix from the new basis to the old basis. Example, consider the following basis of R square. E1 is equals to 1 0 and E1 dash 1 3 E2 dash 2 comma 5. Determine the transition matrix from the basis to the basis E1 dash, means from old basis to new basis, and from new basis to old basis. Solution. Firstly, I will determine the transition matrix P from the old basis to the new basis. So E1 dash is 1, 3. I can write it as the linear combination of old basis 1, 1, 0 plus 3, 0, 1. E2 dash this means that E1 dash is E1 plus 3 E2 because this is E1 and this is E2, and E2 dash is 2 E1 plus 5 E2. So coefficient matrix is 1, 3, 2, 5, and its transpose is my transition matrix na 1, 3, 2, 5. Now find the transition matrix from new basis to old basis. Can you try this?
Yes, ma'am.
Okay.
It is minus 5, 3, 2, minus 1.
Hmm. -5, 3, 2, -5. So next is a small concept which will be helpful in MCQs. Sometimes options are created on this topic also. Ax is equals to b. This was system of equations now. Now I can write x1 as x1 a1. Basically this is first column of matrix A. x2 as a2, and x is x1 x2 so on till xn. Now if solution exists, then B can be written as linear combination of columns of a1 a2 so on till an. This was a1 a2 so on till an. So if solution exists, rank of A is equals to rank of augmented matrix. This implies number of linearly independent columns of A is same as the number of linearly independent columns of augmented matrix. And also in this case, B is dependent with respect to columns of A. And second case is if solution does not exist. This implies rank of A is not equal to rank of augmented matrix. Then we cannot write vector B as a linear combination of columns of A. Now first three chapters, chapter number 1, 2 and 3. One second. One small concept was there. Sylvester's law of nullity. If A and B are two n-row square matrices, then maximum of nullity of A and nullity of B is less than equal to nullity of AB, which is less than equal to nullity of A plus nullity of B. Rank of A plus rank of B minus n less than equal to rank of AB less than equal to minimum of rank of A comma rank of B. This results can be used directly. For example, if I discuss a question on this, T1 is a mapping from R5 to R cube. T2 is also a mapping from R5 to R cube. These are linear transformations such that rank of T1 is 3, nullity of T2 is 3, and T3 is a linear transformation from R cube to R cube such that T3 composition T1 is T2. Then I am asked to find rank of T3. Do you want to try or should I discuss?
Let me see, ma'am, first.
Okay.
Case is hello.
हाँ जी.
मैम प्लीज डिस्कस कीजिए इसको.
So firstly, T1 and T2 is a mapping from R5 to R cube. Rank of T1 is 3. So by rank nullity theorem, this is equal to 5.
Will be 2.
And T2 is a mapping from R5 to R cube. Nullity of T2 is 3.
So rank is 2.
Rank is 2. And I need to find this. So I can apply that note, rank of AB means rank of T3 composition T1 less than equal to minimum of rank of T3 and rank of T1. And T3 composition T1, this is equal to T2 na, means rank of T3 composition T1 is equals to rank of T2. And what was rank of T2? 2. 2 less than equal to minimum of rank of T3. Rank of T1 is 3.
So rank of T3 is 2 or less than 2?
Rank of T3 is greater than equal to 2 na, because T3 was a mapping from, was a composition of one second, T3 was R cube to R cube na.
Yes. So rank will be 3 now.
And from this side also I can apply this na, this part. Rank of T3 composition T1 greater than equal to rank of T3 plus rank of T1 minus 3, because n denotes number of rows. So rank of, and T3 composition T1 was T2, so it is equal to rank of T2 and rank of T2 is 2. So 2 greater than equal to rank of T3 and rank of T1 was 3 na. So by 1 and 2 you can say that rank of T3 is 2. Is this clear?
Yes, ma'am.
Okay.